Good afternoon and thanks for joining. The title of this presentation is called Best Practices for Embankment Construction. My name is John Roach, a senior engineer with the Maryland Department of the Environment Dam Safety Division, and I'll be presenting this topic for you today. This presentation was initially given at the Stormwater Training Program Fundamentals of Success Past, Present, Future on June 4th, 2019. The training program was delivered by the Maryland Department of the Environment and funded in part by the Chesapeake Bay Regulatory and Accountability Program with logistical support from the College of Southern Maryland Center for Environmental Training. Thanks for listening to this presentation on best practices for embankment construction. As we begin, we'd like to ask dam owners and project managers and engineers a few questions to think about during the design and construction process. First, how comfortable do you feel that your dam projects are being constructed properly, both from a contractor side, from the engineering side? Are you confident that your construction inspection is adequate to determine if the plans and specs are being met, and also if the design intent was being met? Are you certain that the contractors know the differences between dam construction and other utility construction? I think you'll find, as we discussed during this presentation, that many entities don't realize the nuances and specialties of dam construction versus other areas of construction. And that highlights itself from some of the submittals we've been seeing in the Dam Safety Division, or that we have been asked to review from a soil conservation district or other delegated authority. We have as-built plans coming in and reports with soil moisture contents well above the optimum. And people are saying, well, I met 95% compaction. But that's not the whole story. That's not all that's important. We've seen some incredible slope distress because of that soil moisture content issues. We've seen folks using geotextiles in their filters and drains, which is a big no-no. But they think they're doing the right thing, and it's common practice in other types of construction to add geotextiles. So people aren't stopping them, though. That's a problem. We're seeing lots of old leaky spillway pipes replaced with new and sometimes leaky spillway pipes because either the pipe is the wrong pipe or the construction methods to install it are improper. We're seeing things like vertical excavations and dam embankments, which can cause differential stresses, cracking and settlement, which can lead to seepage failures, gravel bedding under spillway pipes, and sometimes just pure lack of construction documentation. We've been asked on more than one occasion recently to approve the as-built plans for a small pond where there is completely insufficient construction documentation. And in that case, the owner and the engineer is really asking the department, Dam Safety Division, to take on the liability whether this structure was constructed properly or not. And we're not going to do that. So what we want to do is ensure that people construct their dams properly and maintain them properly. Now, at the same time, I didn't take any dam engineering classes in school, and I suppose most people didn't. In fact, very few universities around the country offer dam engineering classes, and then certainly contractors and inspectors might not be taking those classes or engineering classes whatsoever. And a lot of what we know is that the nuances of dam design and construction are learned over time with experience and with some professional development and self-starting initiative on how to learn them. So there aren't any, and we acknowledge that, but we do want to point out to people there are many resources available to learn about dam design and construction. First, there are many national level publications from FEMA, the Army Corps of Engineers, the Bureau of Reclamation, and the USDA NRCS that have all aspects of design and construction guidance, very detailed, very well written documents, and they're worth reviewing again, both on the engineer side and on the contractor side. I wouldn't have gotten my experience the way I did, both from construction materials testing, geotechnical engineering, and dam safety engineering, without a real lot of cross-training and mentoring, both that I've received and now as I advance through my career that I'm trying to give to junior staff. Because those lessons learned and experiences are invaluable and really can help people understand the specialty of dam construction. So we want to encourage folks who are in the industry to take junior staff under their wings and explain to them what they're seeing, why they're doing what they're doing. We also strongly encourage participation in professional societies and then taking advantage of training opportunities like webinars and technical seminars. American Society of Civil Engineers puts on a few webinars and technical seminars related to dam safety throughout the year, but the two major ones in this country is the United States Society on Dams, USSD, which is a relatively smaller, more industry-focused organization, but it does do some good training. And then the larger Association of State Dam Safety Officials, which is about 3,000 members and does monthly webinars, a number of technical seminars throughout the year, as well as annual nationwide conferences and regional conferences. They are a really wonderful source of training and education. There's webinars on demand, and they're all available for a relatively reasonable fee once you become a member. Membership is also pretty reasonable as well. So first things first, I think, would be to make sure that you're educating yourself about dam safety and dam design and construction before we begin a major construction project. Now, in addition to supporting those organizations, the MDE Dam Safety Division is certainly here for you to help provide technical guidance and other assistance throughout the process. When we issue a permit, we're also going to be out observing construction, documenting construction, and make sure that our regulations and best practices are being adhered to. To further that initiative, we're also releasing, probably by the end of summer 2019, a policy memorandum titled Best Practices for Embankment Construction. Now, folks who are familiar with our dam safety website have probably seen a document called Do's and Don'ts for Pond Construction that has been up on the website for quite a while, and this policy memorandum 5 is going to expand upon that Do's and Don'ts. And it's really going to take a lot of the elements that may be covered in the Maryland 378 quote-unquote specifications, which are really not good detailed specifications, nor are they complete for all aspects of dam design. So it's really going to take a good crack at specifications and do's and don'ts. And it should offer a really good baseline document for people in the dam industry in Maryland. I'll note it's not a design guidance, but it does kind of lead you down the path of good design decisions. Again, it's also not a specification, but I think it could be really fairly easily adapted into a specification format for your construction projects. Each section in the document is structured with a best practices section. Information on what to know before you go. That's for our inspectors or people who are going out to the field to observe construction. Types of documents you'd want to review or standards to become familiar with. And then lastly, some expectations for project documentation and reporting. We anticipate this document will be periodically updated and would encourage folks, once it's released, if you have any comments or suggestions for improvements, we would welcome those and we can update as needed. So the policy has about a dozen or so sections discussing the role of the engineer in charge, clearing and grubbing, subgrade preparation, through earthwork, drains and filters, spillways, and concrete work. So it's fairly comprehensive, but again, it may not cover something specific to your structure, so we'd love to hear back from you and feedback so we can incorporate that into the document. All right, so let's talk about some of our best practices for design and construction of dam embankments. For the folks who operate in the small pond world, I will say, the concept of the engineer in charge may seem like a burden to them. But if you're getting a dam safety permit, the Maryland regulations require that an engineer in charge is designated to obtain your permit. That engineer in charge is somebody who has demonstrated experience in dam design and construction and successful project delivery. It can be a single lead person with a team of supporting specialties surrounding them. That person should be a registered professional engineer in Maryland in good standing, and will ask for a resume of experience to demonstrate that you've worked on projects of similar nature for dams of similar height, design, hazard classification, and age too. Now, that engineer in charge ensures that, and they work from the beginning of the project through the end of the project, so they're really ensuring that all aspects of design and construction are performed in accordance with the plans, the specifications, and industry best practices. So that person might review and approve shop drawings or submittals. They'll review quality control testing reports, and they can assist during construction. If there's changes in field conditions, they propose changes that may need to be reviewed by the permitting authority to accept that or modify a permit, and then they'll compile the as-built documentation. So this person is ultimately responsible for the proper design and construction of the dam. The engineer in charge is not required for small ponds, but we would strongly recommend that owners consider this engineer in charge philosophy for their project delivery. I think the incremental cost of having this person carry through from design through construction is probably minimal, because you probably have an engineer who is providing those services at least through most of those phases of work. But when we approach it with the engineer in charge mindset and designate somebody to fill that role, they can catch problems while they can be fixed. Whether it's poor construction practices or somebody forgetting to document issues properly that lead to difficulty with as-builting, they fill in the gaps in 378. 378 as a document has lots of ambiguities, and it doesn't cover everything. It was really meant for agricultural ponds, and now we're using it for these urban and highly urbanized areas for stormwater management. So it's just not always the right document. They can also help keep construction going. They can help the contractor efficiently work through problems like how to deal with sequence issues or overly wet soils. And they protect the owner's interest at the end of the day, so that, number one, the project gets built properly, gets built on time, and doesn't have a failure down the road, because nobody wants to get a call a year, 6 months, 1 month after a project is completed with lawyers threatening actions or whatnot because something went wrong. And oftentimes what went wrong could have been avoided with that little bit of extra effort. So we strongly encourage people to hire engineers who will serve as an engineer in charge for all projects, whether they be dams or small ponds. All right, record keeping. Now, we had a conversation in our offices before this presentation, and one of my colleagues said to me, you'd be surprised at how important it is to remind people to keep records. You'd think it would be second nature, but it isn't always. So we do want to discuss a little bit about that. Clearly, we want and would expect from an as-built package and as construction is going on, written reports of the work completed by the contractor, observations and tests made by the inspection, and those reports should really be completed daily. I know when I was doing construction observation and testing, if I didn't get that report written by the time I left the site, if I let it sit overnight and thought I'd do it later that night or in the first thing in the morning, I'd forget things. I'd forget where a test was done or what elevation it was, even if I had good field notes that just needed to be transferred into a typed copy. there's always something lost. So written daily reports are really valuable for projects. And we recommend compiling those daily reports and submitting them to the engineer in charge at least once per week, because that way the engineer in charge can see how things are going, can make sure that that any problems are being addressed properly, and if there is something going on that needs some attention or maybe needs rework, you'll catch it before it's too late, before a bad lift of soil is buried under 20 feet of additional soil because the reporting came out a month or 2 months later. We can catch it before it becomes an even bigger problem. Of course, reports should be clearly written and legible, and that's important because we might refer to them later on, 1, 2, 10, 20 years later down the road when we're looking to make a repair on a dam. We might need to know how it was constructed, so typed reports are preferred. We should include the date, time, and weather. Weather factors can be a huge impact in construction, whether it's hot or cold weather and how it impacts concrete curing, or whether it's really dry or really wet and how that might impact soil moisture conditioning. It's important to know. Why did we get all those failed tests because of excess moisture content? Well, it had been raining that day and 2 days before, and the contractor hadn't taken any steps to protect the subgrade. So that's important information. Of course, we want to provide the location of observations and tests. We want to document that with some kind of benchmark for the site, whether that be stationing with offsets and elevations. That way we know where the tests were made. And we want to make notes of if the contractor makes any modifications to the approved plan set, or maybe how they address something that's been left up to a means and methods. How did they handle that subgrade issue? Did they pour a mud mat? Did they put down a base of gravel, which wouldn't be a good thing? Did they over excavate and replace? Take as many photos as you can. Storage space on servers is relatively cheap. We'd rather have more information than less, so more photos are great. And then lastly, I would say include notes about failed tests or rejected materials. Oftentimes, my experience has been that the third-party tester will kind of have a pencil copy of the testing for, let's say, soil density testing, and they won't note a failed test. They'll tell the contractor will address it, maybe by drying out a soil and recompacting it, and then they'll take the test again and note that it passed. But I think those failures and then confirming that the failure has been fixed can be important after the fact, and it provides some insight into how the construction went. So note the failures, and note that the failures were then addressed as well and corrected. This information has proven time and time again to us in the Dam Safety Division to be valuable when dams have a long-term rehabilitation project or they develop a problem suddenly after many years. So it really is, it's not just documenting for the sake of documenting. It's valuable information that helps us all. All right, I want to talk about the approved plan sets as well. When we issue a dam safety permit, the permit incorporates by reference the approved plan set. And it's important because sometimes plan sets might change over time. Maybe we approved something with a May 1 date, but then some changes were made because of, let's say, a stormwater management issue or erosion sediment control issue. Those changes may be inconsequential, but they might be consequential. So it's important to work from the approved plan set, and if changes need to be made to that approved plan set, we can make that happen. The changes really ought to be approved by the engineer in charge, and then that engineer in charge, before the work happens, should at least discuss that change with the permitting or approval authority and get their buy-in. When we do that, we eliminate or at least reduce the possibility of somebody making a field change and they don't understand the design consequences of that change or why they're changing what they did. One of the worst dam failures in the history of this country was the Teton Dam failure back in the mid or late 70s. It was a USBR dam that failed on first filling. And the forensic reports that were done afterward and investigations revealed a few root causes, but one of them was the fact that the designers sat in the USBR offices in Denver, and the field engineers, who had quite a bit of empowerment, were on the site. I believe it was in Idaho, and they were making field decisions and field engineering changes. Now, it's not to say those changes were necessarily wrong, but what they didn't do is maybe consider some of the other bigger picture impacts of those changes. The dam eventually developed a seepage and piping internal erosion problem, and like I said, failed on first filling. I believe it killed about 14 people and had billions of dollars of losses. So we want to avoid that if at all possible. The picture here in the slide presents a good case of a project recently that I was involved in Calvert County, where during our pre-construction meeting, the contractor was there and had some questions about how to construct something on the plans. And we all got together, the engineer in charge, myself, who wrote the permit, and the contractor, and made some markups right then and there. We all agreed to them, and it made the project go a lot easier and smoother for all people involved. So keep track of those changes, keep track of the approved plan sets, and make sure we know what's going on. That's really important. Okay, I'll touch on this subject briefly, but we've had a project recently in Maryland where the engineer, or the contractor, I should say, the contractor on the site thought they could eyeball the location of a manhole on the plan set. They ended up being like 20 feet off of the location. They required extensive additional excavation, and then they had a grade bust. So the pipe had a reverse slope back towards the dam and didn't drain well. That all could have been saved with a real simple call to your surveyor. I'm sure all contractors have a surveyor who they've worked with. So we recommend having a licensed surveyor locate all structures and alignments, mark them out, and expect to maintain those marks as construction goes along. Marks will get damaged. I don't know why, but it feels like bulldozer blades have some kind of magnetic attraction to survey stakes. They get knocked over quite frequently. But it's really important not only for the quality of the construction to have things placed at the right location and elevation, but also from the inspection standpoint, so that the inspector can clearly know the test was performed at this location and at this elevation. Now, a lot of times lately, bulldozers, so many of them have GPS units set on the equipment to help grading process go more efficiently. So maybe elevation control points are a little bit less critical, because the inspector can ask the dozer operator to set the blade down and wait for a few seconds to get an elevation reading. That's fine, but it's still important to have some kind of ground truth benchmarks out there that can be referred to. Okay, on to subgrade preparation and soil foundations. We want to stress that the subgrades should be inspected and approved by the engineer prior to filling or placing structures. Sometimes that may mean including proof rolls or testing as well. We find that oftentimes, especially on dam retrofit projects, the subgrades can be really wet. You've had that water behind the dam there for quite a long time. The subgrade's going to be very saturated. Or in new construction, you're digging down to a subgrade. Maybe you've intercepted a perched groundwater level. You're trying to put in a cutoff. But we don't want these really soft or excessively wet areas underneath the dam. They should really be undercut. We would strongly advise against thick bridge lifts. They work in the sense that they can result in stable working platforms, but now you've got this thick mass of poorly controlled soil, probably in a critical location. It may be a preferential pathway for seepage or promote differential settlement and cracking at a later date. So we avoid bridge lifts where possible. And inspectors need to be aware of that, and they should review the project geotechnical reports to understand what the conditions they should be seeing in the field are. Because if there's a change, they should let the designers know that. But they should also be prepared. Is this a sandy subgrade, a clayey subgrade? Do we expect high groundwater? All of those things can help inform recommendations in the field for how the subgrade is prepared. And of course, as you're inspecting it, please note the subgrade condition, any cleaning that had to be done, removal of poor quality material, and any of the measurements taken or preparation. All right, rock subgrades are a little more tricky sometimes. It really depends on the condition of that rock. If you're in the Piedmont area, you might be in a highly weathered rock, saprolitic condition. And in that case, are you going to treat that subgrade as rock or soil? That's where some geotechnical testing, maybe it's test pits or soil borings ahead of time, will help the engineer decide what the appropriate methodology is. And then that methodology should be incorporated in some kind of project specifications or at least notes on the plans. But when you truly have a rock subgrade, we would recommend to remove loose rock, overhangs, and sharp transitions. What we're really looking for is a firm subgrade where we're going to have good contact with the embankment soils to the rock, good bonding, and we don't want any areas where we could get stress differentials. So a sharp overhang, a sharp transition, when you're placing soil into there and you don't have good compaction control, which sometimes is not the contractor's fault, it's just a geometry issue, you can get lower stress areas in the soil or differential stresses. And differential stresses lead to differential settlement and cracking, and most people have heard of differential settlement before. They know it's a bad thing. And of course, cracking in a dam embankment can lead to all sorts of problems. So again, keep that subgrade kind of nice and even, remove any of the loose materials, and then we want to cut off and seal any of those cracks or joints or discontinuities in the rock. Recommend filling them with dental concrete or slush grout so that we've got a nice impervious surface to work on. But before you place that slush or grout, make sure it's approved by the engineer in charge. Some specifications will be pretty detailed, calling for water jet cleaning of any clay infilled seams or joints. We've seen people with shop vacs, literally with shop vacs, cleaning out, preparing the subgrade in a rock foundation, so it's really ready for acceptance of the embankment fill material above it. So inspectors should review concrete mix design and specs, both for the subgrade prep but also and the cleaning, but also for what might be placed if it's that dental concrete or slush grout. And again, review the project geotechnical reports to understand the expected conditions. What if you encounter a soil subgrade when you were expecting rock? Or what if you have a mixed subgrade, half on rock, half on soil? What should you do there? The photo in this picture is an example of a foundation for a dam in Frederick County, and they actually use shotcrete to prepare the subgrade and make a working mat. That's a rock foundation, but clearly in the photo it looks like there's a lot of soil there, so I wasn't involved in it. I can't speak to the other preparation methods, but the dam has performed satisfactorily throughout its lifespan thus far. All right, on to earthwork. This is one of the areas where it can be the easiest thing, but it can run into the most problems. Soils are natural materials. They can vary from place to place on the site, whether that's the borrow materials or the subgrid that is receiving the fill, and they're really susceptible to moisture and types of compaction. So first, we would recommend, if there are unsuitable bearing materials encountered, contact the engineer in charge and get some direction on what the appropriate method to deal with that bearing material is. Again, we'd recommend not performing bridge lifts, but maybe it's just disking and drying. We wouldn't recommend soil amendments like concrete or lime. That can result in a more brittle embankment, which is more prone to cracking. But there are a lot of options to deal with difficult subgrade materials. or if your embankment fill has been disturbed, maybe overnight or over a shutdown period, maybe due to winter weather and snow or rain or whatnot. If you have to make some kind of an excavation in the dam embankment itself, absolutely would say no vertical excavations. We want 2 horizontal to 1 vertical slopes or flatter. Usually those are some kind of stair-stepped or benches. And what this is going to do is create a good bond between the existing material and then whatever will be the backfill in that excavation. We want good binding and kind of create one single massive embankment again. And vertical excavations tend to create what is called arching effects, where you get poor compaction and then lower stresses, and again, that differential settlement or cracking. We would say that testing of materials for earthwork is very important. Now, I would say that any kind of borrow material should have had a recent test at the borrow pit, less than maybe 1 or 2 months from the time of delivery. We want to make sure what you're getting on site, if it's coming from off-site sources, is what you expect. Or if you're borrowing on site, you want to have sufficient testing, that being Proctor compaction testing, Atterberg limits, and grain size analysis at the least, to understand what compaction characteristics you should expect. Now, when you're placing that material, you want to test each lift for compaction and moisture. Again, 95% compaction isn't always good enough if you've got excessively wet or excessively dry material. So compaction and moisture, standard Proctor always. And we'd recommend 1 test per 5,000 square feet per lift per material, or 1 test per 50 linear feet per lift in trenches. Generally, moisture contents range between -2 and +2% from the optimum moisture content for granular materials, and from optimum to 4% above optimum for cohesive materials. Wetter is often better is a phrase we've heard a lot, and particularly for cohesive materials, because you get less permeability, a more elastic soil, less prone to brittle deformations and cracking. And it can be too wet, though. Too wet, especially in a very sensitive, cohesive soil, can just lead to pumping and rutting and generally bad compaction. All right, we would recommend that the moisture content determined by your nuclear gauge is verified in the lab or in the field periodically with oven dry samples. And this is particularly important in soils in the Piedmont area, which have high mica contents. And the hydrogen bound in that mica is something that can throw off the nuclear density gauge readings of moisture content, and you can get biased high readings. So oven dry samples are a good thing to do, and then you can develop a site-specific correction factor sometimes, so that you can input that correction factor into the nuclear gauge and take away that bias from the high mica content. Again, we mentioned previously on this last slide that recent lab tests are important. I've seen so many submittals from borrow pits or aggregate suppliers where they took a sample a few years ago when they opened up that pit or that material, and they keep on giving it to you. You'll see it in a submittal. The facts that they sent over and photocopied 10 times, they'll be a little skewed and grainy, and the date might be scratched out or it'll be very old. But soil materials are variable. You don't want to rely on a really old test. You want to have something new and fresh for your site. How confident are you that material you're getting delivered is what you expected, what you bought, particularly when it's a manufactured aggregate, because you needed a specific gradation. So grain size, Atterberg limits, and Proctor compaction again. Standard Proctor is the standard for all dam projects, not modified Proctor. Even though modified Proctor is typical for most other construction, It's just less energy. We're not trying to compact the soil too much. Again, that we create a brittle, more crack-prone structure. We would recommend placing soil materials in 8-inch loose lifts pretty much everywhere, unless you're close to a structure when you might need to have smaller compaction equipment, and then a 4-inch lift is more appropriate. And then here's a big one. Impervious cores, according to 378, it's often misinterpreted. What 378 says is that the impervious core must extend a minimum of 4 feet below the invert of the pipe or cradle. But that's a minimum. 378 goes on in another section to say if you haven't intercepted an impervious layer, you need to put in some kind of internal drainage, like a toe drain or a blanket and chimney drain. They don't specifically say what type of drainage, but that's what they're getting at. So the reality is the impervious core needs to extend to an impervious layer. Studies will show how ineffective they are, even when they get almost the impervious layer. If there is that window, then they won't perform as intended. Think of it like in a driving rainstorm, and you're driving your car down the street. Your windows are the impervious core. So would you shut your windows and maybe your sunroof halfway or 3/4 of the way and expect to stay dry? Of course not. You shut your windows all the way through the frame of the car. You cut it off, that moisture, completely, and you'll be happy inside your vehicle. And that's what we're looking for impervious cores as well. So again, the inspector should review and be familiar with the geotechnical reports and the lab submittals, know what to expect from materials on site, because a good lab technician and a good quality control technician is going to know what to expect once they've seen those lab tests. From experience, they're going to know what the compaction characteristics, how these materials are going to respond to moisture, and they can be really valuable in that sense, but they need to have that material accessible ahead of time so they can prepare for their field work. And of course, for each test and each lift, record the location of the testing, the type of compaction equipment used, the lift thickness, number of passes. Record what soil type you're testing for, and then the results of that tests. And like I said before, the failed tests and the retests should all be recorded. Here's an example of a project in Harford County, Maryland, that we got called to. The embankment is oversteep, but also upon reviewing the compaction results, we saw that the material was placed well above optimum. And the combination of those two things resulted in basically embankment unzipping around the entire structure and slumping down. And those cracks extended pretty deep into the embankment and required some major reconstruction. And I think that all could have been avoided or lessened if there had been better control of the compaction. This photo right here I pulled from a forensic report from a dam failure. And it may not be completely evident, but you can kind of see lift lines in here, and you can see some cracking as well, kind of near the text box, a vertical crack. And this cause of failure was contributed in part to overcompaction of a cohesive soil. It was overcompacted and dry of optimum, and it basically resulted in an incredibly brittle impervious core. There was some settlement and cracking, and then an internal erosion failure that happened at the dam. Here's a photo example of a good project. This one is in Harford County, Maryland, about 20 years ago. This is a spillway replacement project from an existing dam that I haven't gotten all the way down to that spillway, because what's in the photo there is the original spillway. But you can see they're sloping the excavation, they're stair-stepping the sides of it, so when they come and backfill around it afterwards, it's going to become a good, solid, uniform embankment and lessen the chances for seepage or other issues in the future. All right, Moving forward to internal filters and drains. I'm going to say this a couple times, but should we use geotextiles? No. Should not be using geotextiles. This is national practice on the federal level for over 30 years now. And basically any major dam organization on the federal level, Army Corps, Reclamation, NRCS, strongly advises against geotextiles in any area where their use is critical for the function of the dam. So can you have a geotextile maybe separating a superficial riprap layer from the underlying soils, where the riprap might be providing like a swale along an abutment groin or along the upstream face? Maybe yes. Would a graded filter below that riprap be preferable? Yes. But should we ever be wrapping our perforated pipes and our internal drains in geotextiles? Absolutely not. Your filter design should be performed beforehand, and it should be part of the project review. But we want to make sure that when you get a manufactured aggregate delivered on the site, confirm with a new sample and a new grain size test that material meets the gradation you're expecting. We had a project recently on a large new dam where the engineer and the quality control person both noticed that the material that was supposed to be concrete sand, clean concrete sand, was a little dirty, and they tested it before use, and they rejected about 5, I believe, dump truck loads of this filter material because it blew past the percent passing 200, the clays and silts specification as required. So the aggregate supplier had to pick it back up and haul it off the site and deliver new stuff. But that was good call and a good catch, because particularly in filters and drains, the presence of fines can really adversely impact their effectiveness. So we don't want that in there. When you've got like a clean sand filter, we recommend 8-inch thick lifts and then compacting them by flooding with water. So we pour water on top of it. Once that water has kind of settled through and leaves the surface, you can hit it with a plate compactor 1 or 2 times. But when you have a really clean sand, that's the best way to get compaction of that material. We absolutely want to prevent contamination. So if you've got construction equipment trafficking over a filter material, or if it's going to be out in a stockpile for an extended period of time, it needs to be protected, because again, these are manufactured aggregates meeting a certain specification, and that specification is being relied on to ensure that there's compatibility between adjacent soil layers. That's an engineered design. So if there is contamination, things won't work properly, so we need to avoid it at all costs. Generally, to do that, we would recommend constructing the filters and drains concurrently with the embankment fill, or sometimes you can build the embankment up slightly and cut a shallow trench and put your filter and drain material in, and then keep on doing that in stages. You would be wasting a little bit of the filter material that is at the interface of each one of those successive lifts because it would be contaminated, but that is an option as well if needed. So again, geotextiles, nope, don't use them in your filters and drains. We've seen them wrapped around pipe quite frequently, and that is not a good thing. It might work initially, but it will clog eventually. All right, we want to confirm that in those filters and drains, you've got a conveyance system to take any collected water out to a safe outfall. So you want to confirm that the pipe material and the perforations meet the plans. If you have too large perforations, they could get clogged up with surrounding soils, or too small perforations, it might not flow enough water. We'd recommend limiting pipe bends to no more than 22.5 degrees. So you want shallow sweeping bends for any of your internal drains. And really the idea there is that video inspection of internal drains periodically through the life of the dam is important, but also once the backfilling is complete and before the end of the project, we would highly recommend that. We had a project recently in Washington County where a dam had received a few kind of band-aid fixes over its life with some corrugated plastic drainage pipe, the kind you'd buy at Home Depot, which is not really the best material for this. But upon video inspection, a few years after this project was complete, we found that the pipes were completely cracked and clogged. Suspect that they probably failed during compaction itself, so they never were really infected. So you want to video inspect, make sure your drains are free of blockages, defects, and all that stuff before your contractor demobilizes. Your inspector should definitely review the filter compatibility computations to understand the assumptions that went into those designs and why you're using, let's say, a C33 fine sand next to a 67 or 68 stone next to the material. All right, here's a picture of somebody flooding a filter diaphragm, and then you can see in the background there's a plate compactor there that they'll also use to compact it once they're done. Example. Here's an example of that toe drain pipe I just mentioned that was a corrugated single wall plastic pipe, not really the best for buried applications for longevity. And the invert of the pipe is kind of on the right side of the screen, so this is a 90-degree skew from the video camera, but you can see the crown of the pipe, the left side of the screen, was just split open and there was material entering the pipe. The pipe failed. All right, we're moving on towards conduits now. After the embankment soils, the preparation of the conduits and installation is probably the next biggest thing you're going to do, where problems can arise, but also where we can prevent future issues with the dam. So we know from historic records that many dam failures occur due to internal erosion. Some people call that piping failures, but that's really seepage along a conduit. Any penetration through a dam embankment, any difference, something that's not this kind of homogeneous soil mass that's your embankment, is a possible location for preferential seepage pathways. And often that's because of poor soil compaction next to those structures. So when it comes to installing conduits, we would recommend not vertically trenching. As we discussed before, if you're doing a retrofit project, 2-to-1 slopes and stair stepping. If this is new construction, you want to construct the spillway first and then fill around it. We've seen a lot of things where utility kind of crews will come in and put these spillway pipes together. They'll put down lintels and gravel as a subgrade and then, put the pipes in and head off the site. And that's not the best idea. That gravel or free draining material as bedding is, again, going to be a preferential seepage pathway that we want to avoid. So we would strongly advise against that. A mud mat is something that can be used if needed, or having it in a concrete cradle if it's a rigid pipe. Pipes definitely need to have watertight joints. For concrete pipe, we'd recommend ASTM C361 pipe as a good specification for your pipes for water tightness, but you can also have metal pipes and plastic pipes, and there are specifications discussing the water tightness of those joints as well. You always want to inspect the pipe to make sure it's the right type and thickness upon delivery. There's often plant markings on the pipe that indicate the type of pipe and what the specification is. It's easy to compare to your project specs, but you don't want the wrong pipe delivered accidentally, or somebody thinking they can get away with putting in pipe type A when really pipe type B is what's specified, because they can look similar. Sometimes it just comes down to the joint profile and details. Concrete pipes should always be supported on a cradle. And when you do have a concrete cradle, we'd recommend pouring the cradles in alternating sections. That way you can ensure that you get complete coverage. Oftentimes the invert of the pipe below there, it's a spot where you get voids or poor compaction of the vibration of the concrete, so you get a pathway there. So by putting it in alternating sections, you can make sure you don't have that issue. Oftentimes flowable fill will be used as a backfill material, and we've learned, and the advice is that you want to place that in 2 lifts because flowable fill has a really high water content. Thus, it's prone to high shrinkage. Not always, but it can be. So by placing that first lift, let's say your goal was to place the flowable fill up to the spring line of the pipe, you might place it halfway or 2/3 to that goal, let it cure, it will shrink a little bit, then place your second lift, and that will kind of backfill any of those voids or separations from the pipe. Those cradles can be poured against undisturbed earth, but if they are formed, we'd batter the sides at a slight batter. That helps promote good compaction with the equipment getting uptight to the cradle and kind of driving the soil into the cradle a little bit, so they get really good bond. We'd also recommend that first downstream joint of the conduit is about 2 to 4 feet from the riser, so that way you don't have cracking if you've got differential movement between the pipe and the riser. Certainly the approved gaskets and lubricants or coupling bands for pipes are important, because oftentimes that's how the water tightness is derived. So if you're using a different gasket or a worn or damaged gasket, you've got a good chance of leakage at that joint. So inspectors really need to be familiar with different pipes, materials, classes, and how they're joined, the different types of gaskets and other materials. You want to check to make sure that joints are properly seated and that there's no damage to the installed pipe. Sometimes if there's improper handling in the field or in the shop, they get edges chipped and cracked, and that can be a problem. One quick and easy check is to make sure that the bell end is upstream. That's always important. And you'd test the concrete cradle as you would any other kind of concrete, and we'll discuss concrete testing a little bit more as we go on. Here's an example of a pipe that was installed with so-called watertight joints. Something went wrong here, though, clearly, because we can see some pretty heavy inflow and what looks like sediment in the invert of the pipe. So something certainly went wrong here, and hopefully that could have been avoided if the construction inspection had been a little more rigorous. Here's another example of a spillway replacement pipe. You can see how it's more or less a vertical trench right up to the edge of the pipe. And you kind of question, how are you going to get any kind of compaction equipment in there to ensure that it's properly compacted? Or if you're going to be placing concrete in there, how are you going to make sure that you really aren't having voids or anything like that? It's just not a good method for this construction. Here's another one where it looks like they built the embankment up and then just cut a vertical trench where the spillway pipe is, and then widen that trench a little bit for some anti-seep collars. I believe I pulled this photo from a case study we have where the pond actually had a seepage incident and maybe a near failure as well, suspected due to this type of construction methods. So avoid this. It's not recommended at all. Okay, I'll quickly discuss this riprap and gabions, because oftentimes we see these used for some kind of outfall stabilization maybe, or an emergency spillway. And this is one of those cases where a separation geotextile would be acceptable in most cases. But you want to make sure that geotextile is placed properly. So it should be placed without wrinkles or bunching. You overlap the upstream piece with the downstream piece. And that way it's serving its purpose. That intimate contact with the geotextile and the adjacent soil is really critical for effective function of the geotextile. So if you've got wrinkles or voids, you kind of take away some of the ability of the geotextile to do any of the filtering that it may or may not be able to do. Don't dump riprap, place it with an excavator. That's important so that you get good interlock between those riprap pieces so that they don't move on you later down or slump down a slope. Same with gabion baskets. Place the rock in them carefully. It can be machine placed. Hand placement is also good, but you don't want to have them bulged out or overstressed, because they won't function as well, and they could end up damaging the basket itself if you just dump things in there. All right, moving on to concrete. So, concrete is often used in the spillway system, whether it's in the riser or as the pipe. So we have a few notes here, and there's some differences for 378 structures to dams. We would generally say precast risers are not recommended across the board, although we acknowledge that they are accepted on 378 structures. And people have questioned me about this before. We have multiple cases in the past where we get leakage, either it's through a precast, the joints between precast risers, or maybe it's in precast box culverts. We get leakage, we get soil movement, migration, and that's just a recipe for internal erosion. So cast in place is much preferred because you can do it properly. You can put water stops in there so you avoid that leakage. We understand that there are some better methodologies, some better materials out there that may make these precast structures less prone to leakage. But I think, the burden is pretty big to get us to approve these at this time. So maybe someday, but I'm not sure we will anytime soon. Particularly with precast box culverts, because of the issues we've seen. I've seen a few photos of them, but never in person, of cinder block or masonry risers. That is definitely a design no-no. If somehow that slipped through or the contractor is proposing a change in the field, that should be rejected right away. Concrete placements should be timed to ensure cold joints are avoided. That's just general good concrete practices, but cold joints are another area where you could get seepage and soil loss and other erosion problems in your concrete. We do recommend water stops. We would recommend the center bulb or dumbbell type PVC water stops, but the manufacturer and the engineer should work together to determine the purpose of that water stop and the location to size the right one and get the right design. These water stops are really your best line of defense between separate pores, and that bulb that can be in them, it can be designed in all sorts of ways to allow for joint movement or whatever is needed. We would typically avoid swell type bentonite water stops. They can work effectively, but they can, if they're not installed properly or detailed properly, they can, when they swell up, they can put some pretty high tension stresses in the concrete and cause cracks, and then they just are ineffective. So water stop installation is something that needs to be performed carefully by experienced personnel. Sloppy water stops are as good as no water stops at all, and we want to avoid that. Now, when you're pouring concrete, before you do that, we want you to check the reinforcing steel to make sure that it's been constructed in accordance with the design drawings, and you want to make sure there's adequate cover here too, because water infiltration into that concrete can cause corrosion of the reinforcing steel and then spalling and other types of long-term issues. We recommend both the design of concrete in accordance with ACI 318, which is the normal code for concrete design, but also applying the ACI 350 requirements, I think it's called for environmental structures, which is just a slightly more robust requirements to deal with these water-bearing structures that are in harsh environments. And I think any application where you're up against water permanently, like in a dam, would qualify for this. So 3 inches of cover is recommended when you're pouring against earth, and 2 inches elsewhere at a minimum. You want to make sure that the concrete is adequately consolidated. You don't want to over vibrate or move the concrete with the vibrator because you can get segregation and poor quality. So again, I mentioned the inspector should review the shop drawings for reinforcing steel, make sure they understand them clearly, understand the mix designs and where different mixes are to be used, because it's a real shame, and I've seen it happen before when you've got a big project going on and multiple concrete mixes at multiple locations, and you pour the wrong mix in the wrong location, and that just causes all sorts of headache because you have to rip out multiple portions of concrete and redo the work, and it's no good for anybody. Also, definitely become familiar with the ACI hot weather and cold weather concreting recommendations, because curing is a vital part of the concrete process. We want to avoid any cracking or damage due to improper. Well, Review those batch tickets. You want to make sure they're not adding excessive water between batching and delivery or batching and discharge. You want to make sure that we haven't exceeded the time requirements from loading to discharge, because you could get some initial set and poor quality concrete as a result. These are all really standard things for somebody who's experienced in concrete inspection. So it shouldn't come as a surprise. It's not an added effort, but we do want to just reinforce those requirements here. And then quality control testing of concrete is critical. We would recommend at a minimum that concrete is sampled once every 50 yards per mix, per placement, per day. Take multiple cylinders, because we're going to take strength tests at 7, 28, 56 days. Some projects you might take even additional cylinders if you're thinking about stripping forms early, or for some reason you want a 14-day break as well. You want to check the slump, the temperature, and the air content on all of these mixes. It's just good quality control and good documentation. You want to document the location of the pour, the mix design, the weather conditions, curing methods, and test results for each pour. And also retain a copy of the batch ticket for your records, because if something goes wrong, at least that can help us trace it back to the plant. Here's a good example of a properly installed water stop. You can see it's halfway embedded in, so that center bulb is partially sticking out of this existing concrete. We've got this rebar cage here that's nicely tied. So we've got this is a base of a riser here, and we're going to be pouring the concrete walls shortly after. But that PVC water stop is mostly free from any kind of latence material or overpour of concrete. At that bend, as opposed to it being kind of cut and spliced and butt welded together, it's got this sweeping radius curve, which is a good detail, because anytime you have to splice and weld together water stops, you've got a potential location for a defect. So if you can just put this curve in there, that's all the much better. I have heard from some folks that there's one or two issues with this detailing overall, but we won't go into that. But this isn't perfect, but it's pretty darn good. Here's an example of a precast box culvert with a leaky joint and material deposition. So that's a case of why we like. And then of course here's a classic picture of some really horrible concrete work. We want to avoid this. Is this going to be a watertight? Is this going to be a long-lasting structure if we've got this poor consolidation and shallow cover on reinforcing steel? It's not good for anybody. So that would be an example of something. Here's a case in a riser construction where I would just note that while the formwork and everything looks pretty good, and I won't comment on the fact that maybe these side slopes are a little bit vertical and unsafe, do look at the subgrade here. You can tell that it's just covered in water and loose mucky soil. So imagine when the concrete gets poured in there, it's just going to get all sorts of disturbed and intermixing with that water and produce a lesser quality material. And ideally what you'd do is you'd have proper control of that before you start putting all the formwork and rebar in, so that you can clean off that subgrade. You can make sure it's properly prepared and free of water. So you'd need to have some kind of diversion, maybe a sump and pump, and do all that before you start doing the formwork and the rebar installation as well. All right, we're almost done here with the presentation, so thanks for sticking around. I want to talk a little bit about valves quickly. Valve work, we've seen some issues lately with valves, and oftentimes it results in excessive leakage, which can result in premature wear of the valve and replacement. And they're often difficult to replace. They can be pretty darn expensive. So, but if they're installed properly and maintained properly, a valve should last a really long time, decades. So it's worth it to do it right the first time. So when you install a valve, you want to make sure the stem is plumb and well supported, so that you don't want that long stem to kind of act like a string of spaghetti. Once it gets torqued, and it will just buckle. You want to make sure that the stop nuts are properly adjusted. So normally there'll be some kind of limit stop nut that will prevent you from over-torquing and over-tightening a valve. We've got a case in Western Maryland recently where the contractor did not adjust the stop nut, and the first time the owner then went to close the gate valve, they weren't familiar as much with the operation of the new valve. They kept on cranking and cracking, and they ripped the valve operator right out of the concrete because of all those forces that are applied to the concrete. But the properly adjusted stop nut would have prevented that from happening. I've had a few cases where the contractor, for whatever reason, disassembled the valve on site. They didn't want to lower it down into the shaft or into the riser structure in one piece. It was calibrated at the factory. It was great in good condition. It never got reassembled with the same factory tolerances, and it leaked like crazy. And it's going to have to be replaced, and my understanding is the project cost is in the many hundreds of thousands of dollars for this one particular project, all because the contractor cut some corners. And I'm not blaming the engineer in charge here for this, but there was a lot of issues where it prevented the engineer in charge from actually coming to the site regularly. And if they had seen this happening before time, they could have stopped the work and avoided this. But there were some project logistical challenges that prevented them from coming out. So there was a few good lessons learned on that project that we've kind of covered throughout this presentation that could have prevented a huge cost occurrence for the owner of that dam. So don't disassemble the valves on the site. And do perform leak tests. We want to make sure that the leak tests, the valve leaks in accordance with it's usually an AWWA standard, because excessive leakage can result in loss of your pond. If it's drinking water or something like that, water is valuable. But also that leakage can cause damage and wear to your valve and the conduit structures as well. Now, it's important for both the contractor and the inspector to understand the shop drawings. They can be intricate for these valves, but there are lots of little pieces that can go into them. Maybe it's a rubber gasket or a wedge or something like that. In the same case in Western Maryland, I mentioned where the stop nut wasn't adjusted properly, there was also a thin neoprene gasket that was supposed to have been installed, and for whatever reason, there was a shop drawing revision. It wasn't provided, and that gasket wasn't installed, and even with only about 14 feet of head on it, we didn't have good bonding between two metal surfaces where the gasket should have been, and we've got excessive leakage from that. But if somebody had seen the shop drawings, they would have called out and said, hey, where's the gasket? And we could have avoided that leakage as well. So here's this example of the stop nut not having been adjusted properly, and you can see how the concrete has just ripped out. This was brand new work, and it had to be replaced, and it cost a month or two of delays in the project as well to get things refabricated and poor quality concrete chipped out and replaced. So case. And this is the same project here, and this is the flow on the completely sealed valve, but that gasket is missing, and you can see how much of an impact that's making. Quite a bit of water flowing through. All right, well, I've covered everything I have for this best practices for embankment construction. I'm not going to say I have everything covered, and I'm not going to say I know everything guaranteed. I've learned a lot. I've been advised from a lot of intelligent people on what they think are good practices. I've taken some of this presentation from various resource documents from other state, regional, and federal partners. So I thank all of them for this information, and I thank you for listening. If you have any questions or comments, or once the document is released and you'd like to see any changes or make recommendations, you can reach out to me at john.roach@maryland.gov, and I'd be happy to discuss any of this with you. And with that, I will wish you a good day, and thanks for listening. All right.